Hello and welcome back to Mr. Viola's Physics Classroom. Today we're doing a special AP Physics 1 homework review from stuff we didn't have time to get to in class. It was 25 to 34 in the forces doc on Google Classroom that we've been working from. So let's go through some of these and make sure that we're all on the same page, we all know what we're doing. So we started with 25. 25 had an A, B, and a C. Let's get those laid out. A wanted you to force diagram what was happening in this situation. So for letter A, we have, as always, the force of gravity, the normal force, an applied force, and a force of friction. And letter B wanted us to find what that normal force was. So in this case, we know that the normal force is equal to the force of gravity. So when I start to figure out what the normal force is, it's dependent on what the force of gravity is because my two vectors are the same size, the two forces are equal and opposite. So knowing that relationship, I just have to look at the mass, which was 24 kilograms, and the acceleration of gravity, which is 9.8 meters per second squared, and I find that the normal force is 235.2 newtons. Letter C wanted us to find the acceleration of the object. So a little more complicated. The net force is equal to mass times acceleration. This is Newton's second law. I know in this case that the net force is the unbalanced portion of the applied force. So in this case it is the applied force minus the force of friction. So when I start to answer this, I can say that the acceleration is equal to the applied force minus the force of friction divided by the mass. So in this case, the applied force was 585 newtons. The force of friction can be calculated by doing the coefficient of friction multiplied by the normal force. So we have 0.23 times 235.2, and I divide that all by the mass of 24 kilograms. And what we should find is that the acceleration of this object is 22.1 meters per second squared. So all of this is based on knowing your relationship between forces. Number 26 was an extremely similar problem. It was basically the same thing. Instead of being pulled, it was pushed, but it's still along the horizontal axis, so you can solve it exactly the same way. So I'm going to skip number 26 and move straight to 27. Number 27, the difference was that we're pulling at, I believe, at an angle this time, and we are. So 27 still has an A, a B, and a C, but this time we're moving at an angle, which means that my force diagram is going to change. So in this scenario, we still have the force of gravity. I still have a normal force, but because I'm pulling at an angle, it's going to be a little bit different. So let's go ahead and put that applied force in, and you can see that I'm pulling up a little bit. Part of that is an upward force. So that means my normal is going to be a little bit smaller than gravity to compensate. And I still have my force of friction going backwards. So that would be my force diagram. For letter B, they want us to resolve the forces of the applied force. We'll move this over here. So if we resolve the forces of the applied force, remember to resolve just means to get your x and y components. So we make our right triangle. The angle that they gave us in this problem was 38 degrees, and they told us that the applied force was 410 newtons. So now this is just some pretty simple trig. This is the opposite side, so I have 410 times the sine of 38 degrees, and this is the adjacent side, so that would be 410 times the cosine of 38 degrees. So when I solve those, plug them into your calculator, 252.4 newtons for the y, and the x is 323.1. For letter C, they wanted us to again find the normal force. And then they wanted us to answer what that normal force does to the force kinetic friction. So we'll do letter C in this purple color. So if I'm finding the normal force, again I look at what my relationship is. Before it was just that the force of gravity equaled the normal force. That is no longer the case because I have this other vertical vector, this vertical part of the applied force. So it's actually going to be something like this. The force of gravity is equal to the normal plus that vertical applied force. So now I want to solve that for the normal, which is just going to be Fg minus Fay. So I have all my numbers. I can just plug right in. Fg is again the mass times 9.8. And I'm subtracting what I just solved for Fay, which is 252.4 newtons. So this gives me a final answer of a normal force of 188.6. And so that asks how that affects not the coefficient, but the force of kinetic friction. Well, we know that the force of friction is based on the coefficient multiplied by the normal force. So if the normal force goes down, then my force of friction also goes down. I'm going to have less friction in this problem because I'm pulling upward as well. For letter D, it wants us to again find the acceleration. So let's put letter D in pink, and we'll put it in place of the force diagram. So letter D, finding the acceleration. Again, I want to find the net force. So the net force is going to be equal to ma, Newton's second law. And I'm looking horizontally because that's the direction I'm accelerating. So horizontally, the net force would be the applied in the x direction minus the force of friction. And so when I start to put in numbers for that, I'm solving for A again. So A is going to be Fax minus Ff over the mass. So I know that Fax is 323.1 newtons. I'm going to subtract my force of friction, and I'm going to divide by my mass, and we should get about 6.4 meters per second squared. So that is my acceleration based on the information I've been given. Number 28 appears to be the same kind of problem. It is not. So let's look at 28. It has a very similar, it is exactly the same numbers, but a very similar way that it's being moved. The difference this time is that it's being pushed. So when you're being pushed, this is 28. When you're being pushed, that just changes this. It changes your force diagram a little bit. And you can see that the normal is now slightly larger because I'm being pushed at an angle instead of pulled. And so when you push on something, you are going below the horizontal. I'm pushing down on it. I'm pushing down at an angle. So this is what my force diagram would look like. Letter B is looking for me to resolve those vectors again. So I have exactly the same number of 410 newtons. It's just that the angle is in a slightly different spot. So still 38 degrees. When I do my sine and cosine, I'm going to get exactly the same numbers I got before. The only difference is this is now negative 250 newtons and a positive 320 newtons right up here. So that's B. We've resolved our vectors. Again, one of them is negative this time, so that's the difference there. Letter C, finding the normal force. Here's where things start to change. I'm going to add the vertical component this time to gravity because it's going down as well. So I'm pushing down, extra, which means the floor has to push back up harder on it to compensate. So if I'm looking for the normal, I just plug in 45 kilograms times 9.8 meters per second squared. And then I can add my FAY, which is 250 newtons. And so I get 691 newtons. Don't be confused by this negative sign, that's simply direction. You don't need to put a negative right here. We've made gravity a positive value, so we're going to keep that as a positive value as well. And then the same question as last time, what does that do to the force of friction? It's going to raise it this time because my normal force has gone up because I'm pushing down to the ground, so it has to push up harder. It's going to be more difficult to push it, the force of friction is going to be higher. Think about if you're pushing something across the road and you're pulling it up a little bit as you go, it's going to be easier. If you're pushing it, it's going to be much harder because you're pushing it into the ground even more. Letter D simply wants to know the acceleration. So we figured out exactly the same way as before. We have the acceleration is going to be the horizontal component of my applied force. So 320 newtons minus the force of friction, which in this case is 0.18 times the normal force that we just found of 691 divided by the mass of the entire, I believe it's a wagon, 45 kilograms. So acceleration is 4.3 meters per second squared. So we have the same numbers. The difference is between a push and a pull, and it's really just the angle at which you're applying a force. If you're pulling it, because of the difference in the normal force, which caused the difference in the force of friction, pulling it, we accelerated at 6.4. If I push it, I accelerate at 4.3. So I accelerate much less with this push than I did with the pull, even though the forces are the same. And then 29, that was the answer to 29, because you're changing that force of friction based on the normal force. 30 through 34 were the same problems as these. So they were the homework half of the assignment. If you have problems with 30 to 34, please feel free to come in and ask, but they are exactly the same as those with just different numbers. Thank you very much for watching. I hope this was helpful.